Welcome to session 108 in the AISafety.com reading group. The presentation tonight is by Vadim Kosoyer, Research Associate for the Machine Intelligence Research Institute. His article on the Learning-Theoretic AI Alignment Agenda has recently won the first prize of round 3 of the AI Alignment Prize. Please go ahead, Vadim.
Okay, so hello again, everyone. And I'm going to talk about my essay, which basically explains my research agenda and the motivation behind it and the general research directions. The overarching goals of the research agenda are the 3 items that I list here, which are the first item is mathematical desiderata of general intelligence, and what it means is developing some kind of mathematical theory that explains what general intelligence is. So in intuitive terms, in the context of AI alignment, general intelligence should mean the ability to pursue certain goals in an unknown environment, effective in some sense. So this is like a one-sentence explanation of what we mean by intelligence, but sort of formalizing this mathematically is
Krishan and Lucas, if you could please mute your microphones.
Sorry, is it muted?
It is not muted. Okay, so everybody, if you look at the picture where the screen should be, there should be a button where you can close the call. 2 buttons to the left, there's a microphone. Press that one, then it should be muted.
Am I muted now?
No.
I was muted before then.
Okay. So if you keep speaking and I'm not currently saying you are not muted, in that case you're probably muted.
Okay, great. So the second item is the mathematical desiderata of alignment. So when we say that in artificial intelligence is aligned, what does it mean exactly? So it should mean that this agent, it in some sense pursues the same values that we pursue or the same goals that we define it in the sense that we mean it. But again, how to formalize this mathematically is a complex question. And somehow my hope, or so to speak, the holy grail of this research program is that eventually this theory will produce a quantitative theory of AGI performance and safety. So somehow the vision is that eventually we'll have a theory which will allow us, given a certain AI design, produce some quantitative estimate of how safe this design is and how good this design is, which of course will have some empirical parameters and some error bars and so on, but at least there will be some theoretical basis for claiming that your design is safe or not safe. And the main building blocks which my agenda builds in is statistical learning theory, computational complexity theory, and algorithm information theory, where just briefly, very briefly, statistical learning theory basically tells you, well, it answers questions such as how much data does an algorithm need, a learning algorithm need to converge to the right answer, and whether it even can converge to the right answer. And computational complexity theory adds to this the dimension of computational resources. So maybe you have enough data, but it's not feasible to process this data with some reasonable amount of computational resources. And so the sum of those two is usually called computational learning theory. And the third part, algorithmic information theory, is basically well, it's basically what tells you what is the correct prior you should use in some sense for your agent to be a truly general intelligence that somehow is able to reason about, in some sense, some as broad domain of problems as the thing that humans are able to reason about. So, okay, so the first part is what I call universal reinforcement learning. And what I mean by this is basically an attempt to answer this first item here, the mathematical desiderata of general intelligence. So the starting point of this is the AXI, which was introduced by Marcus Hutter. AXI is basically an agent that that assumes its environment is sampled randomly from a Solomonov prior. So what is a Solomonov prior? So just in 2 words, basically Solomonov's prior is a way of mathematically formalizing the idea of Occam's razor, right? So when we discuss, just think about what does it mean to think rationally, or use the evidence that you have in rational ways or in scientific ways, then like the central principle there is Occam's razor, which says that a simpler theory is more likely to be true than a complex theory. And Solomonov's prior is a way to formalize it, where like the complexity of the theory corresponds to the length of a program for some universal Turing machine that encodes this theory. So you can sort of imagine the drawing diagram here. It shows you have the AXI agent, and you have like the environment, and the environment gives some stream of bits into the agent, which are the observations of the agents, and this can represent its sensors or whatever input it gets from the environment. And then there are some actions that the agent takes to affect this environment, and so you get some closed loop process here. And then if you assume that the environment, which agent doesn't know a priori, is sampled from the Solomonov prior, then you can talk about the expected utility of the agent, and the agent with maximal expected utility by definition is the AXI. So AXI is sort of an attempt to formalize what intelligence means, and this is like a nice first attempt, but there are all sorts of problems with this. So ultimately, what I hope this theory will give us is it will give us some set of optimality conditions that an agent should satisfy in order for be called general intelligence in some sense. And these conditions, they should be sufficiently strong. So I'll say a few more words about this later. It should be sufficiently general in the sense that the space of environments that your agent can somehow effectively operate in should be like a very big space in some sense. And the sample complexity and computational complexity should be feasible. So as opposed to AXI, which is not even computable, we should arrive at a theory that is consistent with agents that are actually feasible, that can be implemented in some non-feasible computational resources, which is the computational complexity part, and which converge to some. The learning process takes some reasonable amount of time, which is the sample complexity part. Okay, so I'm going to speak about a few problems with AXI, a few problems that AXI doesn't solve, and which are important, in my view, to arriving at this theory of general intelligence. And I'm going to say just a few words about how I think this problem should be attacked and how I'm trying to attack them. So the first problem is the problem of traps. So what is a trap? A trap is an irreversible decision with no long-term consequences. So it's something that you do and which has potentially bad consequences that you cannot undo once you took this action. And this thing creates problems. So most of existing reinforcement learning theory assumes that there are no traps. So why does it assume it? Because if there's a trap in the environment, then it's not clear why you can learn that there is a trap. The only way to know for sure that the trap is a trap is by entering the trap, and then it's sort of too late. You cannot get out of it. So it's not clear how to have some kind of guarantee that your agent can asymptotically learn about all the traps and approximate some optimal performance or something like this. So usually reinforcement learning theory just assumes there are no traps or has some tricks like episodes which resets that just traps are irrelevant in some sense and so on. And like one of the reasons it's especially important in the context of AI alignment is because of a lot of problems that arise in the context of AI alignment, we can think about them as certain special case of traps. So for example, if the agent self-modifies in some way that makes it like it changes, for example, its utility function in some bad way, or just makes it like an ineffective agent, then you can think about it as a type of trap. Like it's an action that your agent can take that will lead to some bad state, and you cannot exit the state because once you took the action, the original agent doesn't exist anymore and replaced by some other agent which will do some bad things. And corruption is also so what I mean by corruption is like, so in reinforcement learning, your agent usually experiences incentives to do things which we would consider bad. For example, if it has some external reinforcement signal which is trying to maximize, then it creates an incentive to hug the signal and to artificially set it to a high value and just decouple it from what the humans actually want. And like entering this sort of states can also be considered to be a type of trap. So how can we try to solve this? So one approach which I investigated and continue to investigate is what I called DRL, which means delegative reinforcement learning, where your agent can sometimes delegate actions to a human advisor, and then you're able to prove that your agent will be capable of learning about all the traps that the human knows exist in the environment, and in particular, it solves the corruption problems under some very simplifying assumption, but in principle, it can solve the corruption problem. So other directions can be introducing some assumptions about the environment or formulating some optimality conditions which are like weaker than what's usual in reinforcement learning theory, but stronger than just bias optimality. Okay, so another problem that AIXI has is the lack of reflection. So AIXI is incomputable, despite that the environments that it's able to reason about are computable, and so we can sort of, instead of AIXI, we can consider some agent whose prior includes only, for example, only environment that have a given time complexity. But then the agent itself will always have a higher time complexity. So Bayesian agents almost always have higher complexity than the environment, and this creates a paradox because the real environment is usually more complex than the agent. For example, it can contain other agents which are just as complex as the original agent. And so we need to somehow take this into account. The theory needs to deal with this. And one direction that I'm exploring is the use of what I call incomplete or fuzzy models, which means that your agent reasons in terms of models that don't fully specify the environment, but specify just certain aspects of the environment. And then you don't need the environment to be more simple than the agent. You just need the environment to have some properties which are simple enough for the agent to express, and then your agent will be able to exploit these properties. So I wrote here also some test cases of how such a theory can be tested. So game theory is like looking at several agents that interact with each other and seeing whether you can prove the conversion to some reasonable equilibrium. Like decision-theoretic problems where you have omega that simulates the agent, and the agent cannot simulate omega, and self-modification is another case. And of course, another important case for AI alignment is when you have a closed loop between a human and an AI, and like at least one of them will not be able to simulate the other. So you need like this theory of, you need some kind of reflective theory of reinforcement learning to prove things about such loops. Okay, so the next part of the agenda is value learning protocols, and here I'm actually talking about alignment itself. So what does it mean for an agent to learn human values, and how can we make sure, can we create setups that ensure mathematically that this learning will actually happen? So there are several ways how you can, in principle, try to communicate values to an agent. And so one way is by what I call formal communication. So formal communication means that you're transmitting some signal to the agent that has a priori known semantics. So it means that the agent, it's sort of hard-coded on some level into your AI what a signal means. So for example, it can be just a full specification of a utility function. It can be a reward signal, or it can be just some comparison, some special cases like you saying to the agent that this situation is better than this situation, or this situation is twice better than this situation, or things like that. So what are the problems with this? So first of all, specifying anything is very hard. So fully specifying the utility function is somehow completely infeasible, because like the human values are very complex. Like it's very hard to specify them mathematically. Like we're very far from there. But even producing a reward signal becomes very hard if you're sort of trying to communicate the sum total of human values as opposed to some specific narrow problem. So this is like one problem with this. Another problem is the incentives for corruption, which I already mentioned before, and like which DRL can solve to some extent, or at least in simplified models. And the third problem with this is scarce information, which means like for example, if I'm just giving a reverse signal to the agent, then it might be that it will take a lot of time for the agent to discover what it's supposed to be doing. For example, suppose I want the agent to prevent World War III, to prevent a nuclear war from happening. So its reward will be, 0 when nothing interesting happened, and -1 if there is a nuclear war, and +1 if somehow nuclear war was eliminated forever. So something like this. But the problem is that the agent will get a lot of zeros in the beginning, and it will take it a lot of effort to reach any state where some relevant reverse signal exists. So this is some limitation of this. So an alternative approach, instead of formal communication, we can do something else, which I call demonstration. So what is demonstration? Demonstration means that the human is just trying to communicate its values by just demonstrating them, by just doing things that are aiming to optimize these values, showing the agent what the agent is supposed to deduce from that, what the values is supposed to be optimizing. So this idea was very popular and remains popular in recent years in different formulations. So there's like inverse reinforcement learning, where agent just observes the human and tries to guess what's the utility function, what the reward function is. There's CIRL, cooperative IRL, when the agent and the human act together simultaneously on the environment. And there's the variant that I introduced, which is DIRL, delegative inverse reinforcement learning, where the agent acts on the environment and can sometimes give control to the human and allow the human instead to act on the environment and see what the human does. So the advantages of this is in some sense easier in the sense that you don't need to specify the utility function, you just need like to do things in some sense. And like it might have richer information because the human that's doing the demonstration is already moving towards some reasonable goal. So from the start, you have some information about what the human is trying to do. The challenges with this is, of course, the demonstration can be imperfect. The human can make just errors during the demonstration, or do some very suboptimal or irrational things. And again, the human can get corrupted. So like the signal from the human to the AI can be hijacked, or the human can be manipulated, and so forth. And another problem is that, or perhaps a related problem, is that it's limited by the capacities of the demonstrator. So, for example, if I'm offered a bet whether to play a game of chess against Kasparov, then I will not take the bet because I know I cannot win such a game of chess. But maybe I would like the AI to take the bet if the AI would act in my stead, because the AI can actually win against Kasparov. But the AI might never be able to learn this because it will never be sure whether I'm rejecting these bets because I don't think I can win, or I'm rejecting these bets for some completely other reason. For example, I simply don't like playing chess or something like this. And like this is related to P versus NP. So giving a reverse signal is like NP. You're just evaluating a solution. And doing the demonstration is not evaluating a solution, it's producing a solution. So the P versus NP problem, the main thesis there is that evaluating solutions is much easier than producing solutions. And this means that in some sense, producing a reverse signal, at least in a computational sense, producing a reverse signal is actually much easier than demonstrating. So one idea I have about how to sort of try to get the advantages of both as much as it's possible is a protocol that I call learning by teaching. And like in learning by teaching, you have three actors. So you have your agent, which is the AI, you have someone called the advisor, which is presumably be a human, and an operator, which might be another human. So the operator acts on the environment, and the advisor gives some advice to the operator. And there are three modes between which the AI can switch on its own. So in one mode, the operator is doing things and the advisor is giving advice. In the second mode, the operator is doing things and the agent is giving advice instead of the advisor. And the third mode, the agent is just acting directly on the environment, and the operator and the advisor don't need to do anything. And so what's the idea here? The idea here is that by giving different sorts of advice, the AI can learn what the operator is trying to do. Because, well, like on the one hand, if you're doing something but you receive advice from someone really smart, then it allows you to solve much more complicated problems than the problems you would be able to solve on your own. So this in principle allows the operator to transcend its usual abilities. On the other hand, the AI can understand which advice is good and which advice is bad because of the basic principle that the operator will simply not respond to the bad advice, or maybe it will try it and then will stop using it, whereas good advice, the operator will keep using it, and the agent will be able to conclude that the operator actually likes this advice and like it's moving it towards the correct goal. And on the third hand, there is still the delegative mechanism which protects us from manipulation, because the AI will sort of sample its advice from the space of advices that the advisor, the human advisor, can produce, and will avoid advice that might be dangerous and might manipulate the operator and make it react in incorrect ways. So in principle, this approach should allow us to transcend the ability of the operator, so give us sort of better results than just usual demonstration, and avoid corruption. So, and you don't need to manually specify a reverse signal. Okay, and so ultimately, I hope that whatever the ultimate protocol is going to be, what I hope is that this protocol will have some philosophical backing by some theory of imperfect rationality. So we're going to have some mathematical theory which tells what does it mean for an agent to have certain values or a utility function or some other representation of values despite the fact that the agent is not perfect, not perfectly rational, and so forth. And like, for example, one model that sort of emerges from thinking about this learning by teaching algorithm is that your agent is going to be not perfect because it has a limited hypothesis space. There are hypotheses that are too complex for it to contemplate. It can become corrupted. So some states, when the agent, the human enters them, it stops just behaving rationally in any sense, and it can just randomly do some errors. And the learning by teacher protocol can sort of overcome, in some sense, all three types of irrationality, overcomes the limited hypothesis space because the AI can have a much bigger hypothesis space. It avoids corruption by the delegation mechanism, and it can avoid the random blunders because when the AI already learned enough, it can act directly on the environment and somehow simulate some perfect version of the operator in some sense. But this is not necessarily the final model, but hopefully we'll have some model which sort of explains what imperfect rationality is. So some other topics that are included in my agenda are, well, one topic is the topic of taming demons. So what are these demons? So demons are unaligned sub-agents. So you might have an agent which is, in principle, which is in principle aligned in some sense or follow some protocol which should ensure a good, which has some performance guarantee in some sense, but it has sub-agents that are not aligned. So how can this happen? So for example, if your agent includes some evolutionary algorithms, then the evolutionary pressure can create some intelligent agent which has some different agenda. Like biological evolution created humans by optimizing for genetic fitness, created humans which optimize for other things. Another example is that your agent might be simulating other agents. It might be just thinking about the world and imagining other agents which exist or might exist in the world, and it runs simulations of this agent. Some of them might be malicious, and some of them might be able to actually escape from this box, which is the original agent. And like the third example is the causal attack of Paul Cristiano, where some malicious superintelligence sort of runs a lot of copies of your AI, which seem like which all of these copies, they see something which looks like ordinary Earth, but there are much more of them than Earth, and it causes your AI to think that it's in that it is one of these copies and it is not on the real Earth. And this allows the malicious superintelligence to manipulate your AI. So I divide these demons into two types. So there are Cartesian demons and non-Cartesian demons. And Cartesian demons are those that just use the usual input-output channels of your original AI to do bad things. And the non-Cartesian agents are all the rest. So non-Cartesian agents are sort of work by trying to hack your AI from the inside, find some error, some bug in the code, in the operating system, in the hardware, or just transmit information outside using some physical effects like magnetic induction or whatever, and use that. And in principle, Cartesian agents should be blocked by the same performance guarantees that follow from the theory that we had before. So like if we will have a theory of universal reinforcement learning plus value learning protocols, which gives us some optimality guarantees that in particular imply that our AI is going to remain aligned, then this blocks the Cartesian agents also, just by definition. Like for example, this causal attack is blocked by delegation because your AI is able to delegate to the human at the correct moment of time and use this to distinguish between this, whether it's in the simulation or really in Earth. So the Cartesian agents are relatively easy, although we have to be careful with the quantitative analysis of our performance guarantees. which is not simple. The non-Cartesian agents, at the moment, it's much less clear how to solve. I do not really see a purely learning-theoretic solution. So one solution that sort of works is just using homomorphic encryption, which is a sort of way to encrypt the execution of your AI in a way that makes it look like just execution of random code. And so under some assumptions, reasonable assumptions about physics, such an encrypted AI will never be able to sort of break out of the box, and you can sort of communicate it by encrypting and decrypting these inputs and outputs, and then like its normal inputs and outputs become the only channels of communication, all the other channels are cut off. But it has like very serious performance penalties, and it might make your AI uncompetitive against some bad AIs. So maybe there are some ways to do, instead of using actual homomorphic encryption, use something weaker, like hardware which has some, with some formal validation that you did on it. But okay, but it is a complicated problem. Okay, and the last topic that I wanted to talk about, and sort of the last sort of item on my research agenda, is self-improving AI. So self-improving AI is the AI that sort of improves itself, and so this idea is interesting because it might lead to some kind of exponential feedback loop where your AI improves itself, and the improved AI improves itself even faster, and so on. But somehow this is just an informal idea. So it's interesting to try to come up with some formal mathematical model of this. And well, and there are some things in the theory that I mentioned before that can be useful here. For example, I already said that flawed self-modification is a kind of traps. So theory which deals with traps can also be used to deal with somehow safety of self-modification. This is one thing. Another thing that you can look at self-modification sort of game, where the players are the set of all possible agents, or all agents that your agent can modify into, and then if you will have this result that I sort of mentioned before, you might want to have, that your algorithm converges into some kind of game theoretic equilibrium, then you can sort of apply it to this game, and then it will imply that your agent will actually do self-modification in good ways in some sense. So it will, it will play its optimal strategy in the game, which means it will self-modify into things it should self-modify into, and will not self-modify into bad things. And another just thought about this is that sort of self-improvement. So it sort of seems hard to understand how to formulate learning theoretically. What does it mean, this sort of feedback loop? How do we think about it? So one way I think which might be interesting how to think about it is that self-improvement is really sort of learning on which hardware you are implemented. Because usually when we talk about computational complexity, then we talk about complexity up to a polynomial, which is why we always talk up to a polynomial, because then it doesn't depend on the model of computation. It doesn't depend on what sort of machine, what sort of computer implements your algorithm. And so eventually we'll come up with some algorithm that has some performance guarantees, and that it will run in some polynomial time, but this polynomial time will not be optimal for the particular computer on which we are going to implement it. So then the self-improvement, we can try to model it as the AI trying to learn on which hardware it is implemented and find, and somehow modify itself into implementation which is optimal for this hardware. And then maybe you can mathematically analyze it and find that under some condition you really have this exponential growth phase that people have been sort of speculating about, or not. Okay, so I think that I finished the presentation.
Okay. Thank you for your presentation, Vadim. If anyone in the audience have any questions or comments, please come with them now, and if you have come up with some more questions while people are talking, then please write them in the chat so we don't talk at the same time. So, who would like to field the first question?
I would.
Please go ahead.
Ali. I just wanted to ask for clarification. I wanted to ask for clarification on the learning by teaching. Why exactly could the AI not just say, hack the advisor to give particularly easy advice or anything like that? How does that prevent corruption?
Mhm. Yes, I understood the question. So, learning by teaching basically uses the same mechanism to defend from corruption, like all the other delegative learning protocols. So the basic mechanism is that, well, first of all, the agent knows that there is such a thing as corruption. So it assumes that some states are corrupted, and if you enter a corrupt state, then you can no longer believe anything. And it knows that it should avoid the states. And the way the tool it has to avoid these ways is by allowing the advisor to act first, and then when it learns the behavior of the advisor, then it understands which things are safe. So the basic assumption is that the advisor will not become corrupted on itself, and the operator will not become corrupted on itself. So if you assume that this advisor and operator, as long as they act without the interference of the AI, they will not corrupt themselves, then the agent can learn this certain behaviors, the sort of behaviors that this advisor and operator display are safe, and the states that they enter during this behavior are safe states, and it can then use this knowledge to also behave in ways that are safe. This is like the basic mechanism.
Okay. Stuart Armstrong had a comment.
Yeah. I just wanted to ask if you're based in Berkeley and if you're going to be there in the second half of August.
Okay, so the answer is that I'm not based in Berkeley. I'm based in Israel, and I'm certainly not going to be there in the second half of August. I mean, I might be there sometime in the future, probably will be at some point, but certainly not this month.
Okay, then we should have a discussion after August, after I've formalized some things there and some comments on your thing. I'll send you one link to something that I did to try and remove a causal trade. You may find it relevant to what you were thinking about.
Okay, so gladly, Stuart, of course.
Cheers.
Okay, there is a question from Linda, or possibly some of the other people together with her, asking if the operator is a human in the value learning protocol.
So in the simplest interpretation of the protocol, yes, the operator is human. You might try to come up with some, in the simplest version, the operator is either a human or maybe some organization of several humans or something produced by humans. But you might also try to imagine some more complicated versions, which are more like a post-Christianos thing, where you have some chain, right, where each sort of agent teaches the next agent in the chain. So I think it might be interesting to think about that also, but so far I haven't constructed any mathematical model which does this thing, but it might also be a useful direction.
Okay, there are other people writing, but I guess I could field one question of my own. There are, as I understand it, three, or at least three research agendas. There is your Learning-Theoretic agenda, there's Paul Christiano's ALBA agenda, and the Agent Foundation's agenda. It seems Paul Christiano's agenda focus a lot on the being very strictly competitive with the best machine learning techniques, deep learning, etc. Whereas the Agent Foundation's agenda is all the way to the other end of the spectrum, with not focusing on performance at all, and just trying to find a feasible solution. It seems your Learning-Theoretical agenda is somewhere in between. Is that a reasonable characterization?
So I think that you could say that in some sense it is in between. So it is similar to Paul's agenda in the sense that I'm using mostly sort of conventional or relatively conservative mathematical tools and formalism, so which are usually which people develop for machine learning. It sort of different from Paul in the sense that I'm more focused on. So Paul seems to be focused on constructing some informal solutions which are good enough in some sense, and then somehow gradually formalizing them later. My focus is more on doing things where you can actually prove theorems in completely rigorous way, even if the theorem is initially in some very simplified model. So I prefer to start with a very simplistic model, but about which you can actually prove things rigorously, and then gradually move on to more and more complex models, rather than sort of imagining the final solution and only then trying to make it rigorous. And also I'm sort of focused on reinforcement learning, while Cristiano prefers to sort of a more roundabout approach, where instead of dealing with reinforcement learning, he thinks about things like systems that answer questions and things like that, which somehow in a roundabout way allows to create systems that can act on the world. So and like the agent, on the other hand, on Mir's agenda is well, it's similar to mine in the sense that it also tries to construct some formal mathematical theory, but it's different in the sense that well, the mathematical tools in Mir's agenda and the sort of the sub-problems that they emphasize are different from the tools that I use and the emphasis in my agenda.
Okay, Rafe had a question in the chat. I don't know if you can see the chat. Does the advisor have to be completely benevolent? What if it advises the operator to do something because it's good for the advisor but bad for the operator?
Well, at the moment, I'm assuming that you know, everyone, all the advisor and the operator are both benevolent. So I'm not trying to think about any conflict of interest between the humans. So it might be interesting at some point of the future, or maybe even it's important some of the future, but think about scenarios where you have several humans that have like different interests and are sort of trying to pull the AI in different directions. But I think that this is like from my point of view, it's some kind of second order effect. Like we need to, if we don't even know how to solve the problem, and you know, in the case where all the humans are perfectly benevolent and cooperative, then going beyond this is somehow seems too ambitious at this point.
The next question from Alexander is about the relationship between homomorphic encryption and the AI box problem. This is something we've actually read in the AI safety reading group paper about, I think half a year ago about or something. So I could get the reference, but Vadim, could you sketch how that works?
Yeah. So I'll say. To try to explain it briefly, so homomorphic encryption is a way to well, execute a program in an encrypted form, encrypt both the program and both the input, and you get an encrypted output that you have then to decrypt. And the property it has is that if someone who doesn't have the key looks at the computation, then this someone cannot distinguish between this computation and just some random program that is running on some random input. And why is this okay? So why is this good for sort of boxing AI? Because it means that if you execute your AI in this encrypted form, then, well, you see, if we assume that the universe is also limited in computational resources, and like it seems like it is, so from our understanding of physics, the universe is in some sense in the complexity class BQP, so it can only do things which are in some sense running quantum polynomial time, which should still be not enough to break the encryption scheme, probably, although it's not proven, it's conjectures, but assuming it's not enough, then it means that the universe, the physical universe, will not be able to tell will not be able to distinguish between the program that runs inside the box and just some random program. And this means that this program will never be able to have any unintended side effect on the universe, which, any side effect that it would have, just running a random program would have. So it just cannot optimize the universe in any bad direction.
So if you had purely information theoretic encryption, like a homomorphic encryption, I'm not sure. Maybe I'll just read the paper. Could you send it to me, Sam?
Yes, I'll send you the paper afterwards.
Yeah. Okay.
In the meantime, I have another question, which is this. It seems this learning theoretic agenda, it's mostly probably limited to AGIs, agents that are based on learning. There are other options for artificial general intelligence, agents that are search planning or based on logic. Do you see, could they be aligned with some of the same methods?
So my point of view is different. So I do not see this agenda as limited to a particular type of agent. And I think this is actually important. So the starting point of my agenda is thinking about what sort of mathematical desiderata can be satisfied by any sort of agent. What desiderata are impossible and cannot be satisfied, what desiderata are possible and can be satisfied, and then and then we can say something more detailed, more quantitative about the satisfaction of these conditions. So I'm trying to get at the mathematical conditions that some algorithm should satisfy in order for us to call this algorithm an intelligent algorithm. So it doesn't matter what is inside the algorithm. From the inside, the algorithm might use neural networks, it might use formal logic, it might use something that we don't even know about currently. But the point is that if we prove some theorem that something cannot be satisfied by any algorithm, then it doesn't matter. No algorithm will be able to do it. On the other hand, if we prove that that some criteria can be satisfied, then it can be satisfied. Then it doesn't matter how we did it. The important thing that we said was that we actually satisfy this criteria. So my point of view is sort of trying to characterize what does it mean for an agent to be intelligent, rather than study the properties of particular algorithms. Yeah.
Yes. I don't think there's been... Lucas has just written a message. In the list of problems with AIXI, I didn't recognize anything that looked like the ontological identification problem. Is that a problem you consider important?
Okay, so this is an interesting question. So the thing is that this ontological identification problem, it is possible that we can, in some sense, avoid it. But so why is it possible that we can, in some sense, avoid it? Because okay, if you have some agent that has some ontology about the universe and its values are defined in terms of this ontology, then you can probably still explain its behavior in terms of some utility function that is defined just in terms of actions and observations. Because the beliefs that the agent has about the objects in its ontology are a function of the observations that it has seen, and therefore we can translate the utility function from whatever ontology the agent is using intrinsically to the space of actions and observations. And therefore, if we so it might be enough to just look at agents that only look at actions and observations, and then if we have in particular a value learning protocol for some agent, then such agent will be able to learn values without somehow explicitly dealing with the ontology thing. On the other hand, it might still be interesting, because this translation of utility functions from some ontology to action observations can, starting from some simple utility function, produce some very complicated utility function with some less good mathematical properties, then it might be useful to do the opposite, which means trying to model this ontology thing explicitly, and then, for example, we can think about it in terms of an agent which plays a stochastic game. So an agent interacts with the environment the agent interacts with something which represents its internal value ontology, and this something is acted upon some other agent which represents the external environment, which represents nature, so to speak. And then our reward function can be a function of the states inside this ontology. So I think this mathematical model, in my view, captures sufficiently nicely what it means to have a values defined as some intrinsic ontology. And then we can ask what sort of regret bounds we can prove in this formalism, and what implications does it have about value learning, and so forth. So I think that this is an interesting research direction. I'm not currently sure whether it's a high priority or less high priority, but certainly it's something that also we should think about.
Okay, I have another question. One thing that your article didn't talk about was the concept of corrigibility. It seems like the addition of corrigibility would make a lot of these value transfer protocols easier, in the sense that if the agent was sufficiently corrigible, the problem of transferring the values would be simpler, in that if we did not hit such a narrow target, then that doesn't matter so very much if the agent is corrigible.
So personally, I don't like the concept of corrigible very much. And the reason I don't like it is because I feel that it is not sufficiently formalized, and I feel that to the point that I think that different people use it to mean different things. So it's not even specified on the informal level, not mentioning the formal level. So the general method of my research agenda is that the way we arrive at alignment is by proving some performance guarantees, which, for example, can take the form of regret bounds, and these performance guarantees they should imply that your agent converges to the optimal value of the utility function, where the utility function is the correct utility function of the human in some sense. So this is sort of the way I'm trying to mathematically formalize the concept of alignment, and to prove that certain algorithms are aligned. So from my perspective, if I manage to prove this, then I don't need corrigibility, or you can say that you can just say that this is what corrigibility means, if you want. And if I cannot prove it, then I don't see how corrigibility is going to be enough. So at this point, I just don't see it as a very useful concept on top of the concept that I already introduced in the agenda.
Okay, we are nearing the end. Alexander has a question about further to this homomorphic encryption scheme, and I don't know if you have any, if you can read it, if you can have. Yeah.
Yes, I can read the chat. So follow-up question: is there a possibility results are unconditionally secure homomorphic encryption? In other words, can we only have homomorphic encryption schemes that we need to assume the adversary had poly time? Well, you need to assume something, right? So, like, if the adversary that is trying to break the scheme has unlimited computing resources, then it can always sort of try all possible keys, for example, or something like this. So in general encryption, there is such thing as like information theoretic description, like one-time paths and things like that. But information theoretic encryption doesn't help you here, because for information theoretic encryption to work, you would need to block the passage of information between the AI and the universe in some way. But this just seems physically impossible, because like there's no way you can, you can completely eliminate flow of information. So okay, so in some sense, the other approach that I mentioned, formal verification, it's not really encryption, but you can sort of think about it as this sort of information theoretic security attempt, because so the idea there is that we sort of have a model of our hardware, and we formally prove that inside this model, the communication bandwidth from anything inside the computer to anything outside is bounded by small constant, and then we will have some learning-theoretic, game-theoretic analysis which shows that this constant is good enough. But then again, to have something like this, you still need to assume physics. So your analysis would still assume a physical model. So I don't see any scheme that will not assume anything about physics, because like this seems almost by definition impossible. I might be missing something, but I just don't see how it can be done.
Okay, I think we are just about ready to wrap up. So the final question would be from Lucas, asking if you have written anything about ontological identification. So unfortunately not. So this is a topic. So I just did not have time yet to address this topic. So there are many things. I believe that I will write something at some point, but currently I don't have anything written yet. Okay. So I will just say good luck, of course, with your research agenda, and thank you very much for coming here tonight. We've enjoyed it very much, and then to everyone, if you want to join next week at the same Wednesday, 6:45 UTC, we'll be reading the article "The Malicious Use of Artificial Intelligence" and discussing that. And otherwise, I will just say thank you for tonight and see you next week.